In this work, we exhibit a strong link between the frequentist PAC Bayesian bounds and the Bayesian marginal likelihood. Since its beginning, the PAC Bayesian theory claims to provide PAC guarantees to Bayesian-like algorithms. However, it is still mainly used as a frequentist theory. That is, under the assumption that the training set contains IID samples from a data-generating distribution, it provides probably approximately correct type of bounds. A PAC bound says that with probability 1 minus delta, the loss of a predictor f is upper bounded by a certain function epsilon. Epsilon is namely function of the empirical loss. The Bayesian flavor of the PAC Bayesian theory comes from the fact that it considers a prior and a posterior distributions over a class of predictors. Instead of bounding the loss of a single predictor, it bounds the average loss of all the predictors according to the posterior. The bounding function epsilon now relies on the expected empirical loss and the Kullback-Leibler divergence between the prior and the posterior. There is many versions of the PAC Bayesian theorem. Most of them are valid for losses in 0,1, like this one adapted from Catoni's work. An interesting aspect of this theorem is that to minimize the bound, we only need to minimize a linear trade-off between the empirical loss and the Kullback-Leibler divergence. It is well known that the minimization is obtained by a Boltzmann distribution, where z here is a normalization constant. In order to study the Bayesian inference techniques with the help of the PAC Bayesian theory, we proceed the following way. Given a Bayesian likelihood, we define a negative log likelihood loss function. When we use this loss function into the PAC Bayesian theorem, and we write down the PAC Bayesian optimal posterior associated to it, we recover exactly the Bayesian posterior. We realize that the normalization constant at the denominator of the PAC Bayesian posterior corresponds to the well-known Bayesian marginal likelihood. From there, it is easy to show that we can rewrite the marginal likelihood as the common trade-off of the PAC Bayesian theory, which is a combination of the empirical loss and the Kullback-Leibler divergence between the prior and the posterior. In conclusion, we have shown that the Bayesian marginal likelihood minimizes some PAC Bayesian bounds. Please read our paper for more discussions, results, and experiments.